Welcome to the second lecture in our Introduction to Chemical Reactor Design module, part of the Catalyzed Transitions to Chemical Engineering course. In this lecture, we'll be beginning in Chapter 5 of the Vogler text, focusing on isothermal reactor design. Here, the overall goal is to tie together the things we learned in our previous lectures so that we can develop an effective algorithm for sizing reactors based on incorporating knowledge about conversion, stoichiometry, and rate laws. General approach that we'll be using will be independent of the type of reactor involved. In each case, we'll be starting with the general mole balance. Now, of course, that will vary depending on if we have a batch reactor, a CSTR, or a PFR. But this is our starting point. We use our design equations for the appropriate reactor. We then determine our rate laws, which we said we should determine empirically, but once that information is known, we can write our rate law in terms of concentration. Then we would like to put our concentrations in terms of conversion. This is conversion with respect to our limiting species. We're going to call that A in this case. And then finally, we'll plug in our expression for the reaction rate into our design equation so that we now have our design equation rewritten in terms of conversion. And with that, we can then determine either the time, if it's a batch reactor, or the volume of the reactor in the flow case required to achieve a specific target conversion. This will be our approach, again, regardless of the type of reactor. And now we'll begin by looking at each type of reactor individually, beginning with the batch reactor. So we'll start off simple, considering a first-order batch reactor. So we have a first-order reaction. A goes to B, and we can write our reaction rate, the rate of consumption of our limiting species A, as KCA. In this case, we're again focusing on a batch reactor, so the goal is to determine the time required, i.e. how long we want to leave our reactants in the reactor for in order to achieve a desired conversion here in a constant volume isothermal batch reactor. And we'll be developing an algorithm where we begin, again, with the mole balance, substituting our rate law, rewrite that to account for stoichiometry, combine everything together, and then evaluate. So we begin from our batch reactor design equation, which we've seen before in its very general form. Again, rewritten here. Next, we need to expand upon our rate law. We have our first order reaction here. After that, we want to account for stoichiometry. So we want to convert all of our concentrations with respect to conversion of our limiting species, again, in this case, A. So we've seen this expression before. And now we're going to combine everything together and rewrite our original design equation, in this case, as a function of conversion. Once we've done that, the next step is to evaluate. So in this case, again, we want to solve for the time it would take to achieve a certain target conversion. So we can begin to simplify our expression. We divide by the number of moles initially, volume over the number of initial moles. That's equal to 1 over the initial concentration of A. Our concentrations cancel. We now then have an expression, dx dt is k1 minus x. And we can begin to solve that by collecting like terms. Okay, so we'll bring our conversion over here with dx. We separate our integral, and now we're going to integrate. In this case, we're integrating from time 0, when we first add our reagents to the reactor, up until the time, how long it takes to proceed from a conversion of 0 to whatever our target is. In this case, since it's an isothermal process, we know that K, our rate constant, is a function of temperature, but it's isothermal, so that's a constant. We can take that out. And then we can evaluate the integral, okay, as such. And once we apply our limits, we then have a nice equation that describes how long it would take to achieve a conversion of X. So this is the first order case for the batch reactor. How about when we have a second order reaction. So now what's changed? Our rate law has changed. Now it's a function of Ca squared, but everything else remains the same. We have the same design equation. Okay, we have our updated rate law. We have the same stoichiometric relationship. All those become combined, and we see now a small difference here in that our Ca naught is squared and our 1 minus x is squared also. Process then is the same. We simplify our expression as best we can. We then separate and integrate. Okay, so our integration now is going to be slightly different. But this is the type of integration that you should be familiar with, or if you need some help, there are some basically references in the back of the textbook to help you out. Either way, once we evaluate that integral, we get a similar but different expression now to account for the fact that we have a second order reaction rather than a first order reaction. But either way, we have an algebraic expression that can tell us the time it takes to achieve a target level of conversion. So those are a few examples of how we can apply the algorithm to our isothermal batch reactor. Now let's consider the approach for an isothermal CSTR. Here, let's similarly begin where we assume we have a first order reaction. A goes to B. Here's our rate law. And in this case, it's a flow reaction, so we're trying to determine the volume of the CSTR required to achieve a certain level of conversion. And we'll be following the same algorithm. Okay, we'll begin with our mole balance, substitute in our rate law, account for stoichiometry, combine and evaluate. Okay, in this case, our mole balance is different. This is our general design equation for our CSTR. We have the same rate law, we have the same stoichiometric relationship with respect to our limiting species. These did not change just because the reactor type changed. Okay, these are a function of the reaction. But we similarly combine these, and now we have a nice simple algebraic expression that can tell us what volume of reactor we need to achieve a target conversion. Okay, we can simplify that a little bit further if we like, okay, depending on what information we have available. Okay, now if we have a second order, again, our design equation has not changed, our stoichiometric relationship has not changed, but the rate law has changed, and we see the implication that has on our final equation here. And you can imagine using the same approach for a third order reaction or fourth or so on. Now, how about the case for two CSTRs in series? Well, we can write the design equation for each one. Okay. In this case, notice that the inlet concentration, the outlet concentrations are what's changing. Our rate law is the same, but we must account for the concentration in said reactor. Combining those, we can get unique expressions, okay, for the exit concentration in this case as a function of the entering concentration and the residence time in the reactor. Okay. We see the same basic form of the expression, okay, but what's changing is the inlet and the exit concentrations between the two CSTRs. Ideally, we want to be able to write our final expression, though, with respect to what's coming in to the overall process. Okay, in terms of what's leaving the second CSTR, that's a function of what's entering, or in other words, what's leaving the first CSTR. So if we plug in now for Ca1, okay, we can write an expression that describes the concentration leaving the second CSTR, assuming we have two equally sized CSTRs and that they're operated at the same temperature and have the same resonance time. If we extend that further and assume we have not one or two, but n, okay, where n could be as high as infinity, numbers of CSTRs in series, then we can write a general expression to describe what's leaving the nth CSTR as follows. Now, what about conversion? Typically, we want to know what is the conversion, overall conversion for the exit stream of our process. Well, we can then substitute in an expression describing that. And when we do that, we can see this nice closed expression to describe the conversion, final conversion leaving the nth reactor as a function of the number of reactors in series. All right, let's consider the other type of flow reactor, or PFR, and we'll also see the analogous relationship for the PBR. Here we'll begin by considering that we have a second order reaction. So here's our reaction, A goes to B, A is our limiting reagent. Here's our rate law. We'll begin, as always, with the design equation, as we've written here for our PFR. We have our rate law, the stoichiometric relationship has not changed. We can combine these things together to write our design equation as a function of conversion. Separate, collect like terms, simplify a bit, and integrate, and now we can get a nice expression to predict the volume of the PFR required to achieve a target conversion for this second order reaction. In the case of a PBR, again, we focus not on the volume, but on the weight of catalyst required. And you can see we get the analogous relationship describing the weight of catalyst required to achieve a target level of conversion. So far, we've been considering liquid phase reactions. Now let's consider what happens in our PFR if we have a gaseous reaction. In this case, if we have change in moles, that can then change, that then changes the volume and therefore can change the concentration of our species. So we have to account for that here as we're doing in the denominator. Then combining that, okay, we can see that in accounting for that potential change in moles, okay, we can rewrite our second phase, gas phase second order reaction, or PFR, as follows. If it's a first order, we use the same relationship for our stoichiometry, but our rate law has changed, and the reaction, the final equation would come out as such, okay, allowing us to again predict volume as a function of conversion. Okay, so far we've been considering what happens when we have no temperature change, isothermal, and also no pressure change. And whereas we may be good at keeping temperature constant through heat transfer, heat exchangers, and such, it can be difficult, especially in a pipe tubular reactor, to avoid pressure changes. So let's see what effect that has and how we can account for that and where that's important. So first of all, why would pressure change? Well, as we have a fluid traveling down a pipe, okay, we can have friction between the fluid and the surface of the pipe, and this can cause a pressure drop. Okay. Now, that's not going to necessarily affect our liquid phase reactions, because as pressure changes, that really doesn't impact concentration due to the fact that liquids, being much more dense on a molar basis, are essentially incompressible. But for gas phase, where molecules are further apart, these are compressible fluids. And so if we have changes in pressure, positive or negative, that will affect concentrations. So how can we account for pressure drop in a plug flow reactor or a packed bed reactor? Well, we need to account for that in our rate law expression. So here's, for example, is a rate expression for a first order reaction. A goes to B. Okay, so the rate of consumption of A, and now we see these additional terms here to account for changes in pressure versus the inlet pressure, and also potentially changes in temperature versus the inlet temperature. And if we consider if our pressure drops, P becomes less than P naught during our reaction, that effectively has the effect of reducing the concentration of our reactant and therefore slowing down our reaction rate. So pressure drops can really slow down our reaction. So how do we account for this in our overall design equation? Well, let's consider a packed bed reactor where the effects are even greater. So we need to now account for changes in pressure in our concentration, our stoichiometric relationship, as we combine that then, in this case, for a second order reaction. We can get an integral to describe changes in conversion over changes in weight of our catalyst as such, and we can solve those equations once we have an expression for pressure as a function of distance or catalyst weight in our reactor. To solve that, we can use the Ergun equation. Okay, so in other words, we need, as I said, an equation to describe how pressure is changing as a function of catalyst weight. And that gives us another ordinary differential equation. So in order to solve these problems, we can't do so easily by hand, but we'll need to solve these coupled ordinary differential equations together simultaneously using something like MATLAB.